Hello everyone and welcome to Maclean 360. In this video I want to explain the concept of curved bars. Let's look at this problem. So we've got a steel bar which is 50 millimeters in diameter, and then this steel bar is formed into a circular arc of 4 meters radius and then support an angle of 90 degrees. Now, a couple is applied at each end of the bar, which changes the slope to 95 degrees at one end relative to the other. So we are to calculate the maximum bending stress due to the couple, or in other words, some bending moment, sort of. So we are to calculate that bending stress from that couple. So E is given as 200 gigapascal. How can you solve this problem? This problem is pretty much simple and straightforward. Now, the first thing to look at is this question is actually a curved bar problem. So you have to first of all look at the radius of the arc which is formed, and that radius is given as 4. So so a circular arc of 4 meters radius. So the radius is 4 meters, right? Basically the same as 4,000 millimeters. And then you were given initial angle which was 90. So theta is 90. But then after the couple was applied, there was so basically think about this as you have an arc and you further bend it due to a couple. So we expect that the angle will further increase. And so it was actually increased to 95. So let's say our final angle, which is the original plus some small change in angle. So they always write theta plus delta theta. So that is 95 degrees. And then E is 200 gigapascal. So our Young's modulus, which is 200 gigapascal, is the same as 200 times 10 to the power 9, which in other sense is also 200 times 10 to the power 6 times 10 to the power 3. This 10 to the power 6 here is megapascal, which is also the same as Newton per millimeter squared. So please, you have to be careful whenever you are dealing with some of these things, okay? 1 megapascal is the same as Newton per millimeter squared. Essentially, our E is actually 200 times 3 and then Newton millimeter square. Even if you don't get this correct, the question will be wrong. That's why I'm taking my time to do all of this. So now that we have the E, let's basically use the formulas. So we have a strain, which is form of the angle. So this is the relationship. The change in angle divided by the original angle is equal to the change in radius divided by the new radius. So so basically we are trying to compare the relationship between the angle formed and then the radius. Okay, so it's going to be so we are trying to find the new radius. So the change in radius is very simple. The change in radius is going to be the 95, which is the new, divided by the original, which was what? 90. So the change in radius is 5, but the original is 90. So 5 divided by 90 will be equal to the original radius. Sorry, the change in angle, please. The change in angle is the theta. So delta theta is sort of the change in the angle. So the new angle minus the original angle, and then you divide by the original angle, which is equal to the original radius, which is 4,000, minus the new radius, which we don't know and which we are after. So solving for R1, this is basically algebra. So 5R1 is 90 times 4,000 minus 90 R1. So essentially R1 is going to be, or let me take my time. So 95 R1, 90 multiplied by 4,000, and then basically I will just divide dividing both sides by 95. So in effect, R1, which is the new radius, is going to be oh sorry, okay, yeah, so 90 multiplied by 4,000, and then we divide this by 95. So essentially the radius sort of decreases. So basically what happens is that as you bend in, so the radius decreases, but then the angle increases. So that's essentially what's happening. So we have 3,789 let's say 0.47 millimeters. So that's the new radius, but we are not after the radius. The question said we should calculate the bending stress. Okay, so we are not necessarily after the radius, but we are after the bending stress. Okay, so what next? Now that we have the radius, we can sort of try to find the bending stress. Now, two ways: either we find the strain. Okay, so this is what we have. So when we see the stress, it is the Young's modulus multiplied by the strain. So two things: either we separate and find the strain, or we just put everything together. But then I think we have to put everything together, and by doing this, the strain, the formula for the stress is actually given by E. So E y 1 over the new radius minus 1 over the original radius. So that's essentially the formula. So as up to this point, we have everything, but we don't have the y. It is important to know that the y is what we call the fiber distance. So let me quickly explain the fiber distance. So let's say you have a cross section like this. Let's say this is the arc. Let's say you have an arc like this. This arc is a circular cross section. Okay, so it will have some sort of so this is the theory. The theory is that whenever you have a member, what happens is that if I apply the moment, okay, if I apply the moment, there is always going to be some portion which will be in tension, and then some portion will be in compression. Okay, but then for this problem, we have been asked to find the stress, so I just want to solve it straightforward. When we say the fiber distance, that is there is a sort of neutral axis. So the line that I have drawn here is what we call the neutral axis. Now, the distance from the neutral axis is thought of as fibers. So we have several fibers. The maximum of all the fibers is a distance which will come all the way. So in simple terms, the fiber distance ends up becoming the centroid. So for instance, if you have a rectangular cross section, if let's say you have a rectangular cross section, the fiber distance, let's say there's a neutral axis here, the fiber distance is that distance from the neutral axis, okay? And the maximum is when you get to this point here, okay? And so that distance is the centroid. So if you have a circular cross section, your fiber distance becomes the d/2, which is, in other words, telling us that if I have the diameter, so let's say if the whole of this is the diameter, then the fiber distance, the maximum of all the fibers, is actually that halfway of the diameter, which is what? The radius. I hope the concept is clear. Apart from this concept, the problem has been is simple, but I just want to explain the y. So the y is the fiber distance, and for a circular cross section, the fiber distance is the radius. That's all, or the diameter divided by 2. So knowing this, we can say E is 200 times 10 to the power 3, and then the fiber distance, which is now 50 millimeters divided by 2, because we said the diameter was what? So 50 millimeters in diameter. So that's all. And then 1 over the new so 1 divided by the new, which is 3789.47, minus 1 over the original, which is what? 4,000. So this question is actually simple and straightforward, but you have to understand the fiber distance. Okay, so what is the answer then? So 200 times 10 to the power 3, and then I will multiply this by 50 divided by 2, and then I'll multiply this by what? So 1 divided by 3789.47, and then minus 1 divided by 4,000. So yeah, so that is it. 69.44 Newton per millimeter square. So in other words, in terms of megapascal, 69.44 megapascal. So that is the bending stress. Thank you very much for watching.